Alright, in this video I'm going to walk you through a few example problems where we're doing calculations with a normal distribution. And the reason I want to show you this is because, of course, not all data, in fact almost no data, is actually going to show up and be a perfect standard normal distribution. So I want you to be able to see how you can convert a given given normal distribution into the standard normal distribution so that you can use either your standard normal table or your calculator to do some calculations. So here's the first problem that I'm going to show you. I'm taking this out of a textbook that I found. The problem says, a forester measured 27 of the trees in a large woods that is up for sale. He found a mean diameter of 10.4 inches and a standard deviation of 4.7 inches. So that's where the normal distribution that I've displayed up at the top of the slide comes from. Remember, the first number is the mean, the second number given is the standard deviation. The problem also states, suppose that these trees provide an accurate description of the whole forest and that a normal model applies. Now, the first thing we're asked to do is to draw the normal model. So of course, we always want to draw our horizontal axis first. Then sketch out our normal curve. Ooh, that wasn't very good. Try that again. Slightly better. And then anytime you draw out a normal curve, of course, the important information is where the mean lies and what the standard deviation is. So in this case, our mean is 10.4. And then we want to indicate where our standard deviations are going to occur. So the first standard deviation will be about here, the second one here, and I'm going to be satisfied with just showing 2 standard deviations. And so, of course, to get these values, we need to add 4.7 to the mean and then subtract 4.7 from the mean. So if we travel 1 standard deviation above our mean, we'll be at 15.1 inches in diameter, and if we travel 2 standard deviations above our mean, we will be at 19.8 inches in diameter. And then likewise, if we travel 1 standard deviation below the mean, we'll be at 5.7 inches in diameter, and then a second standard deviation below the mean will be at exactly 1 inch in diameter. And really that's all you would need to sketch out. There's your normal model for this particular situation. Now the second part of our question asks, what percent of trees will be less than 1 inch in diameter? So if we go back to our normal model, we can see that 1 inch, or a 1 inch diameter, occurred exactly 2 standard deviations below the mean. So that's a very tiny amount of our overall distribution. But how can we calculate that exactly? Well, the answer is that we're going to have to standardize this data. So we're going to need to find the z-score. Now remember, from a few days ago we talked about the z-score, and that's simply your data point minus the mean divided by the standard deviation of your data. So in this case, the data point we're interested in, or the value we're interested in, is 1. We subtract the mean of 10.4, and then we divide by our standard deviation of 4.7. And that gives us a z-score of, give me just a second, and conveniently that turns out to be a z-score of exactly -2. Since I don't have a whole lot of room on this slide, I'm going to erase that calculation. I'm just going to jot down that z is equal to -2. I'm going to take a moment and erase the rest of this calculation so I can show you how to graph for yourself a little diagram to figure out the answer to this. Okay, so now that we've figured out what our z-score is for this particular situation, it's generally a good idea to sketch yourself a standardized normal curve and then plot in that z value that you just found. So here's our curve, and we're interested in a z-score of -2. So if here's our mean of 0, remember this is a standardized curve, here's maybe our standard deviation of -1, actually that'd be slightly to the right of there. Here's standard deviation of z-score of -1, excuse me, and here's our z-score of negative 2. So again, we are interested in figuring out what is the area to the left and below the curve at our z-score of negative 2. So as you can see from the diagram, just like we saw from our regular normal model, it's not going to be a very big area. It's going to be a pretty tiny percentage of our overall area under that curve. So now that we know sort of what our diagram looks like and that our z-score is negative 2, we can take a look either at our standard normal table or we can use our calculator. And again, since I haven't shown you how to do this on the calculator yet, we're going to have to use our standard normal table, which is right here. So if we have a z-score of exactly negative 2, then I go down to the row that includes negative 2, and I look at the column 0.00. So the proportion of observations in our standard normal table that would fall at or below a z-score of negative 2 would be 0.0228. So the answer to our question is, of course, 2.28%. Okay, the next part of this question asks, what percent of trees should be between 5.7 and 10.4 inches in diameter? So this is a slightly more complicated question. If we look back at the normal model that we drew out before, this time, instead of being interested in what's below 1.0, we are interested in what's between 5.7 and 10.4. So this area right here. Now in your book, if you read through that this few pages, what they're going to say is that you should always, of course, draw out your normal model, which we've done here. But you might not necessarily need to do that in every situation. I would always recommend drawing out the standard normal model, though, that corresponds to what you're looking at. What we really need to do, though, is figure out the two z-scores that are going to correspond to 5.7 and 10.4. Now, you might already know what that is, just based on your understanding of the normal model, but let's walk through and make sure we see where these z-scores are coming from. So our first value that we're interested in is 5.7. So 5.7 minus our mean of 10.4 divided by our standard deviation of 4.7, and that's going to give us a z-value of negative 1, which of course shouldn't be too shocking since we saw earlier that 5.7 corresponded to being one standard deviation below the mean. And also, probably not shocking, for our second data point, the z-value, or the z-score that we are interested in is 10.4 minus our mean of 10.4 over 4.7, which is, of course, just a z-score of 0. So those are the two z-scores that we care about. So if we sketch those onto a standard normal model, here's our axis, here's the curve, and our two z-scores that we care about, again, are a z-score of 0, which in our standard normal model is, of course, the mean. So that's going to be right there. And then the other z-score was negative 1. So that's one standard deviation below the mean, which is going to be right about here. And so, of course, the area that we're interested in is this area shaded in red, which corresponds to the area that I shaded on our normal model for this particular problem. So like we've already done before, what we need to do now is either refer to our standard normal table or use our calculator to figure out the proportions that correspond to these two z-scores. So let's look at the value of a z-score of negative 1. So if we have a z-score of negative 1, that's going to correspond to a proportion of 0.1587. So that means that in our model, there would be 15.87% of our data would be to the left of negative 1. Now we need to go back to our table and look up our proportion for a z-score of 0. So we'll get rid of this. And for a z-score of 0, since 0 is right in the middle, it's the mean of our standard normal model, you can either look at the table for the negative values or the positive values. So let me show you what I mean. If our score is 0, then of course I'm looking at this row and this column, and the proportion is 0.5, which shouldn't be too surprising. Half of your data will be below that point, and the other half will be above. If you looked on the other side of your table at the positive z-scores, you'd get the exact same thing. Your z-score of 0.00 gives you a value of 0.5. Again, not shocking. So let's make sure we interpret this correctly in our model. We already said that 15.87% of our data should be below a z-score of 1. We just said that 50% of our data should be below a z-score of 0. But that still doesn't quite answer our question. What we care about is what falls in between -1 and 0. And you can probably see that. To calculate that value, what we're going to have to do, I don't have much room left, I apologize. We're going to take our value of 0.5 and subtract off 0.1587. And so that's going to give us an area of 0.3413. So that's the answer to this question. 34.13% of our observations will fall between the mean and 1 standard deviation below the mean. We have one more part to this question. It asks, what percent of trees should be over 15 inches in diameter? So if we go back to our normal model, we saw that 15.1 inches would be 1 standard deviation above the mean. So we already saw that, like I just said, 15.1 inches in diameter would be 1 standard deviation above our mean. Now we can think about this problem in a couple ways. If we're only interested in giving an approximate proportion of trees that would be above 15 inches in diameter, perhaps using 15.1 as an approximation would be sufficient. Now if you recall from our last problem, we were able to figure out the proportion of observations that would fall below 5.7, and that was 15.87%. So because our normal model is symmetric, that should also tell us that on the right side of our distribution, we'll have 15.87%. So if we're interested in the percent of trees that will be or have a diameter above 15.1 inches, our answer to that question is 15.87% of our trees. However, in this question, we're not interested in 15.1 inches for the diameter. We want exactly 15 inches. So we know approximately what our answer should be, about 15.85%. But let's try to be a little bit more exact. So I'm going to draw in our standard normal curve. We know that our mean, of course, is at 0. But let's figure out what our z-score is for a diameter of 15 inches. So we take 15, subtract our mean of 10.4, divide by our standard deviation of 4.7, and we get a z-score of 0.98 approximately. I had to round slightly on that. And it shouldn't be any surprise that our z-score is just slightly below 1, since 15.1 inches is 1 standard deviation above the mean, and 15, of course, is just shy of 15.1. So here's what we are wanting to find. And we want to know what is this area under the curve above a z-score of 0.98. So we're going to go to our standard normal table. And since 0.98 is positive, of course, we need to look at the positive side of the table. So I'm going to look at the row that contains 0.9, look at the column that contains 0.08, and the intersection of those two is 0.8365. Now remember, even for these positive z values, the proportions that you're getting from the table is the proportion of observations that will be to the left of the z-score that you're interested in. So, I've already forgotten it. 0.8365 is the area under the curve to the left of 0.98. 0.8365. So that's over here. But that's not the area we care about. We care about what's to the right of 0.98. So like we've already done a few times, we just do 1 minus 0.8365. And that gives us a value of 0.1635. So it's exactly 16.35% of our trees should have a diameter of greater than 15 inches, which, like I said earlier, is pretty close to our approximation of 15.87. All right, now I've got just a couple more examples that I want to show you, so please bear with me. Let's say that you're given a problem where you're not having to standardize the score. So you're not given the z-score, I should say. You're actually asked for, or you're given the percent of observations that fall below a certain z-score, and then you're trying to find out what that z-score is. So here's an example. We've got a standard normal model, and we want to know what value of z, so what z-score, cuts off the lowest 12% of the standard normal model. So again, with any problem like this, I would highly recommend drawing out a little normal curve. And we are interested in figuring out what z-score, so it's going to be something over here to the left, is going to cut off the lowest 12% of our curve. So we want a z-score that corresponds to an area under our curve of 12%. Well, just like with the other problems we've been doing, there are two ways that you can figure this out. You can use the standard normal table, like we've been doing, or I'll show you in class tomorrow how to do this on your calculator. So let's take a look at our table. The percents that we're given, or the percents occur on the inside of the table. So in this section, we're trying to figure out what the z-score is. So it's sort of like we're working backwards from what we've done so far. Now, because we know that the z-score we're interested in is going to be towards the left of our curve, we know it's going to end up being a negative value. So I'm going to look in this section of the chart with the negative z-scores. So what I'm going to do is look in the chart for the proportion that is as close to 12% as possible. 12% might not exactly occur in the chart, but we can get relatively close to it. And so if you look up here, these are all proportions that are pretty tiny, less than 1%. As you move down, the proportions get bigger. In this area, we're looking at proportions that are around 5%. If you look way down at the bottom, we're getting close to a z-score of 0, so those proportions are in the 40 to 50% range. So obviously we need to look somewhere in between. And right here in this region is where we want to focus our attention. As you look across the columns, you'll notice that the proportions are decreasing, which is a little bit backwards from what you would normally think. Normally we read left to right. But you can see, like here, I've got 11.5%, which is close to what I'm looking for. I want 12. So now if I go down to the row below it, I'm at 11.5%, so I'm getting closer. Notice here are the two proportions that are on either side of what the z-score that I'm interested in. So we can do a little bit of extrapolation. 12.1% is associated with a z-score of negative 1.17. And 11.9% is associated with a z-score of negative 1.18. And since 12% is smack dab in the middle between 12.1% and 11.9%, so that was negative 1.18, I can say that the z-score we care about is smack dab in the middle of those two z-scores I wrote down above, so it's negative 1.175. And so just like that, we've got our answer, negative 1.175. Let's try another example. This time, we want to know the value of z that cuts off the highest 30% in our standard normal model. So, as we've been doing already, we're going to start off by sketching in a standard normal curve. Here's the mean of 0. And we want to cut off the highest 30%. So that means we're going to be somewhere over to the right, maybe about in this region. We don't know what z is, but I know that this area under the curve needs to be 30%. Now here's where you need to make sure that you really understand what's going on here and what's happening in that standard normal table. As I keep saying, those values, the proportions out of the standard normal table, are the proportions to the left of z. So we don't want to look for the value, the 30% proportion in our standard normal table, because if we did, we'd be looking over here in the negative values of z. That's where that would occur. Let's see. 30% is right around here, and we'd get a z-score of negative 0.50, which obviously doesn't make any sense. We need a positive z-score. So that means that instead of looking at, or looking for a proportion of 30%, we need to look at 1 minus 30%. We need to find the proportion that's closest to 70%. So let's go back to our table. Of course, we want z to be positive because it's going to be to the right of the mean. And so we start looking in our table, and we're looking for values that are close to 0.7. And here I've got 0.6985 on one side and 0.7019 on the other. So 0.7, of course, falls in between the two. If you wanted to do some exact extrapolation to figure out what the precise z-score is, you could do that. Otherwise, you can just estimate. 0.7 is about halfway in between. Our z-scores are 0.52 and 0.53. So you could estimate that to be a z-score of 0.523. That would be completely acceptable. Okay, last example. I'm sorry if I'm boring you, but we're almost finished. Similar type of question. In a standard normal model, what value of z cuts off the middle 50%? So we're not looking for the lowest 50 or the highest 50. We're looking for the middle 50%. So you need to be careful on questions like this. So as I keep doing, we start off sketching in our curve. And I'm going to put our mean of 0. And we want the middle 50%. Now we already know from the 68, 95, 99.7 rule that if I go one standard deviation above and below the mean, then I will have included 68% of the data, which is more than we're interested in. We just want the middle 50%. So we're not going to have to go to quite one standard deviation above and below the mean. It's going to be a little bit, our z-score, whatever it is, it's going to be a little bit less than 1. So there's the area that we're looking for. But of course, we need two different values for z to figure this out. So let's take a look at the picture, and this is why the pictures are so important. If I've shaded in the middle 50% of our distribution, well, how much of the distribution do we have left? Of course, it's 50%. And since our distribution is symmetric, that means I have 25% over here on the left side, and another 25% over here on the right. And this is important because it's this 25% that's going to let me figure out what this value is of z. I need to look for the proportion 0.25. So I'm going to go back to the standard normal table. And let's see, it looks like 0.25, or the closest value to 0.25, shows up right in here. Again, 0.25 doesn't exactly show up in the table, but that's okay. 0.2514 and 0.2483 are approximately evenly spaced on either side of 0.25. So the z-scores that we're looking at are negative 0.67 and negative 0.68. So I'm pretty comfortable approximating this proportion is, or this z-score, excuse me, as negative 0.675. So there's one of our z-scores. Now you probably have realized or have accepted by now that since our standard normal model is symmetric, if we're looking at the middle 50% and one of our z-scores is negative 0.675, the other one had better be positive 0.675. And there are the two z-scores that we were looking for.